Let's please welcome Aamir Shafi.
Hi, thanks, Phil. Can you hear me?
Yes, yes.
Okay, excellent, excellent. Thank you so much. Right, so today I'll be talking about scaling large language model training using GPU-based compression in the MVAPICH library. So we have heard my colleague talk about compression support in MVAPICH, and the focus of this particular talk is how do we utilize that for optimizing LLM training. So here is the presentation outline. I'll just begin with an introduction, give some background, talk about some of the motivation and challenges. Then we'll talk about the hybrid compression design that we have come up with, and then some performance numbers, and then I'll conclude the talk. So large language models, as all of us know, are proving to be really efficient and powerful in different domains, natural language processing, computer vision. I think the capability of these models is dependent on the number of parameters. So, the more the number of parameters, apparently these language models are, more smarter and are able to perform better than, their versions that work with smaller number of parameters. So if you're training a large language model with, say, billion parameters, then we require different parallelization strategies. These would help us scale training jobs to thousands of GPUs. Obviously, this would be much more memory efficient. The GPU's memories are limited, and it's not possible to fit everything into the memory of a single GPU. And also, we need some techniques to optimize communication, right? So if you're training with hundreds and thousands of GPUs, there is obviously pressure on the interconnect bandwidth, and we need strategies to essentially mitigate that. So I'll just zoom into different parallelization strategies that are used by state-of-the-art training frameworks today, and I think these are known as 3D parallelism. So 3D basically means that three dimensions of parallelism, starting with data parallelism. And in data parallelism, we basically make a replica of our whole model, and put them on different GPUs and use different input, mini batches to train the model with. And this is basically, this is typically when we are using data parallelism, we require, gradient synchronization using an operation called all-reduce. So I think I would like to emphasize this particular figure here. I'll just try to explain that, we have different dimensions going on here. So starting with data parallelism, these gray bigger boxes are depicting data parallelism, right? So the whole model, right, which happens to be these yellow boxes, are replicated on this process 0 as well as process 1. And this particular network has, has total got eight layers. These are the first 4 layers, and these are, the second 4 layers. So if we go down the y-axis, we are basically carrying out the forward propagation. And at the end of forward propagation, we, engage in gradient synchronization. And this is where we utilize, all reduce operation to do that. And then this is followed by, going up the vertical axis. And this is basically back propagation, right? So this is the first form of parallelism that I think most of us are already aware of. But the other approaches used by 3D parallelisms are pipeline parallelism and tensor parallelism. So the pipeline parallelism here is depicted. Let's say I'll just focus on the left hand side, process 0 here, that we are dividing the full model into two pieces. And how are we dividing that? We are basically dividing that through the network layer. So the first 4 layers is basically what we call pipeline stage 0. And then the next 4 layers from 4 to 7 are what we call basically stage 1, right? So, and when we are carrying out forward propagation, essentially, once we have produced activations at layer 3 at, pipeline stage 0, then we need to pass these on to, let's say, the layer 4 at stage one essentially. And for this reason, we'll utilize, point-to-point communication here. So once we are going down, we'll use this point-to-point communication to communicate activations, but during the back propagation, obviously we'll utilize this point-to-point communication to communicate gradients. But we also go one step further in tensor parallelism. And in tensor parallelism, what we basically do is that, we have, I'm just looking at this pipeline stage one. What we are doing here is that we are splitting the layer into pieces as well. So for example, these layers, network layer 4 to 7, we have split them into two pieces. This is the blue part and then this orange part. And then we also have these optimizer states that we have essentially sharded. So all of these, again, as I've mentioned, these different stages require different forms of parallelism, require support for different collective communication. Data parallelism makes use of all reduce. Pipeline parallelism makes use of point-to-point communication, typically non-blocking. And tensor parallelism, frequently requires all reduce and all gather operations. And essentially, at the end of the day, pipeline parallelism is doing distributed matrix multiplication on different devices. So some of the state-of-the-art frameworks like Megatron LM, for example, they would combine these three different forms of parallelism, and collectively these are known as three-dimension parallelism. So if we now look at something like DeepSpeed software, and DeepSpeed has this technology called Zero Optimizer. It basically takes the parallelization of data parallelism to a next step, right? So it basically has this three levels of zero technology: 0.1, 0.2, 0.3, and essentially if we focus on this top right of the slide here, we have, this is basically the top row here is the baseline, right? So each GPU in the case of data parallelism is storing parameters, the blue portion. It's also storing gradients, and it's also storing the optimizer states. But as we are going down, so this is 0.1. In 0.1, this optimizer state, the green bit, is also sharded across the GPUs or the devices. And then 0.2 basically takes this one step further. It shards gradients as well, and then this 0.3 further partitions the model parameters that are stored in the case of data parallelism. So what is the impact of doing this? So for example, with these predefined hyperparameters, if the baseline is, let's say, consuming 120 gigabytes, 0.1 approach would, each device would require around 30 gigabytes. And if we, use the most aggressive 0.3, which is also the most communication intensive, then, the memory utilization comes down to 1.9 gigabytes, right? So I think at the core of DeepSpeed Zero approach is that essentially this all reduce operation is broken down into, kind of stages. First, an all gather is performed, which is then followed by a reduce scatter operation. And, between all gather and reduce scatter, basically forward propagation or the computation is essentially being performed by different devices. So in this figure, we are just looking at the impact of communication on the overall training, right? So the top right figure here is showing the proportion of compute versus communication for different kinds of DL training workloads. So the first bar here is a DeepSpeed mixture of expert, then ResNet. This is simply PyTorch, and then we have a deep learning recommendation model. So, and as you can see, the blue part here is the compute, and there is significant communication part there as well. And if we just zoom into the communication part, right, we can see that communication consists of broadcast, different kinds of collective primitives, all gather, all reduce, all to all. And as we heard in the keynote talk, deep learning, recommendation models, as well as a mixture of expert rely significantly on all-to-all operation. These, these strided green boxes here. And as we all know, all-to-all is the most communication intensive because everybody in the room is essentially talking to everybody else in the room. So this is the most communication intensive and hence more difficult to optimize. Okay, so what does this mean for LLM training? All of this, right? So LLM training. So the fundamental observation, or sort of the idea behind the work that I'm presenting here is that we are communicating different types of data when we are doing, let's say, data parallelism or pipeline parallelism or this tensor parallelism. And mainly we are talking about these three data structures: gradients versus activations and optimizer states. And the fundamental observation here is that the gradients are generally very sparse and they are mostly zeros. So we have more room to play with them. However, activations and optimizer states are more dense, and hence we have to be careful. So if we are doing anything like using compression for compressing these different data structures, we have to be careful with activation. We have to be more careful with activations and optimizer states versus gradients. And what this means in terms of compression is that we can actually utilize what we call lossy compression for gradients, but we have to use at either high rate lossy compression, or we have to use lossless compression for activations and optimizer states, right? So essentially the whole idea in this particular work is that we'll basically see, is it possible to use GPU based compression in MVAPICH and let's say improve the bandwidth and the throughput of LLM train, right? So this is what this slide is depicting, that using compression assisted MPI collectives. So in MVAPICH we have support for different types. I mean, we have support for point to point as well as different types of collective communication with compression. That so can we use that for accelerating large language model training? For this particular study, we are using 3D parallelism in a 0-1 setting. And if you recall from the previous slide, 0-1 is the first stage of deep speed 0, where we only shard the optimizer state. And I mean, in terms of memory, that has the most impact because that's optimizer state is the most consumes the most amount of space on the GPU. Right. So some of the challenges that we encountered in this study, like what are the major communication routines involved in typical 3D parallelism? So I've given an overview of that, and how to efficiently utilize different sparsity inherent in the messages without compromising accuracy. Right. So I will be presenting some results where I'll give you an overview of the impact of using lossless and lossy compression on this kind of workload. And how do we avoid over compression in certain parallelism degree, right? So basically, how again this is to do with essentially, are we using compression, is that leading to a drop in accuracy, and how, if so, then how do we essentially mitigate that? Right. So with now I move on to the hybrid compression design. And so we have different designs here, and the first one that we call MZ hybrid. The name is a little bit strange, but yeah, I'll explain this. So in MZ hybrid, essentially the word hybrid should show that we are mixing lossless and lossy. So in MVAPICH we have support for both lossy and lossless compression. And I mean, as the name suggests, basically the lossy compression means that if you are giving me, let's say, a float or a double, I will convert that into compressed data. I'll communicate that, and the receiver would basically do decompression, but they won't get the 100% the same data as the sender. There will be some loss, in of the data, right? And in terms of lossless compression, you'll be at the receiver and you'll actually get 100% same bits as the sender has sent from the sender side. So with the advantage of lossy compression is that this obviously gives you better performance. So you can predefined in libraries that, I'm communicating, let's say, a float, which consists of 32 bits. So, I'd like to, communicate, compress this into, let's say, 16 bits. So from 32, compress this into 16 bits. This is all predefined, and the ratio in this particular case is going to be 2x, right? If I compress data from 32 bits to, let's say, 8 bits, then, I'm basically compressing it 4x. So the compression ratio in this particular case is 4x. And in the case of lossless, you don't specify like how much can it do. You just leave it to the library and the algorithm or the compressor to do the best job for you. In our experience, typically in scientific applications, lossy compression would give you better performance. Lossless would give you, it won't have any impact on the accuracy. However, typically they won't reduce the data as much. Again, this 100% depends on the application that we are targeting, because all these different compressors, they would just look at the data. They would see, is there repetition in the data? Is there sparsity in the data? And based on all of these factors, they would, give you the compressed data. But typically lossless, we have seen that, it gives you around 15% to 20%, compression ratio, which is significantly lower than lossy ZFP. So in this case, what we are doing here is that for these different stages, right, for data parallelism, we're using all reduce, pipeline parallelism, point-to-point, tensor parallelism, all reduce and all gather. And for zero stage one, we are using all gather and reduce scatter. So in this setting, we are using ZFP, which is the lossy compression scheme for data parallelism, because we know here, we could go a bit aggressive because we are just communicating gradients. And the nature of the data is that, that it will be able to, it will be able to, we'll be able to sustain that loss. However, when it comes to pipeline parallelism, tensor, or zero stage one, we are utilizing this lossless compressor called MPC. So compare this with Z hybrid. Again, in this case, we are not using MPC at all. However, in Z hybrid, we are using low rate ZFP for data parallelism for this all reduce, which is communicating gradients. However, we are using high rate ZFP when we are, for pipeline parallelism, tensor parallelism, and zero stage one. So now over to some performance evaluation. So here is the performance experiment setup. So, application is LLM training. We are doing this with DeepSpeed and Megatron LM. Both of these work on top of PyTorch distributed. The communication library here is MVAPICH 2 GDR, which has support for ZFP, lossy, and MPC, which is a lossless compressor. So we are training this GPT Neo X 20 billion parameter model. This data set is books 3, and pipeline parallelism degree is 6, model parallelism degree is 4. The gradient accumulation step is 1, which means that, at every iteration we are doing all reduce, and the micro batch size per GPU is essentially 8. And this is done on the Larsen cluster, which is a Power 9 system, and this is equipped with a Tesla V100 GPUs. So here is, the base, basically starting with the naive compression, so to say. And in naive compression, what we basically mean is that we have, so the left graph here is throughputs, samples per second. So basically higher is better. And this is throughputs, T-flops per V100. Again, this is also higher is better. And this third graph here is showing the test loss, right? So and y-axis, the x-axis here are the steps, and then the y-axis here is basically the loss. So if we just look at the left figure first, the baseline is giving us a certain performance, right? It's scaling well, which is good. We're going from 24 GPUs to 192 GPUs. And then we look at how are we doing with naive ZFP 16 and naive ZFP 8, right? So ZFP 8, which is the orange bar, is the most aggressive. It's basically compressing every FP32 into 8 bits, right? So basically the compression ratio is 4 times. If I'm communicating a message, the message size is getting reduced by 4x, which is great. So obviously it's giving me the best performance here. But when I look at the accuracy, accuracy of these experiments, we can see that the ZFP8 version is performing the best, right? Is performing the worst, right? So really, we first of all, we need to make sure that whatever compression technique we're using, we're actually getting the same loss trends, and then we'll come back and look at the throughput or the performance. So this is basically starting from naive compression, which is using ZFP. And then on the other side, so the other extreme is going to be use lossless compression. So since there is going to be no loss in accuracy, we should be able to get exactly the same performance as the baseline. And as you can see in this accuracy loss, that is actually true. But when we look at the throughput, or when we look at the throughput in terms of T-flops per GPU, the lossy version is actually slower than it's actually doing worse than the baseline, right? So this blue bar is actually lower than this the green line. So which basically means that yes, it's giving me the best accuracy. We need something in the middle between using aggressive lossy compression or using lossless compression. So and this is where the two approaches that I've introduced earlier, they basically come in, and now I'll just present some results with them. And the first approach here is what we call MZ hybrid, right? So MZ hybrid was that we are using for all reduce, we are using ZFP, lossy compression, right? But we are using for tensor parallelism and pipeline parallelism, we are using lossless. And as we can see here, so I'll start with the accuracy chart, and you can see that the 8-bit version and the 16-bit version, they are actually coming very close to the blue, the baseline, which basically suggests that the accuracy is acceptable in this case. And when we look at the performance results, we basically see that compared to the baseline, we are actually seeing around 5% increase in the performance, right? So which basically means that these are basically acceptable numbers and good numbers. So now some results from the Z hybrid approach, and please recall that Z hybrid is fully lossy compression. We go less aggressive with all reduce and more aggressive. I think I said that the opposite. We go more aggressive with tensor parallelism. We go more aggressive with all reduce data parallelism and less aggressive with model parallelism. So, and in this case, we see really good performance, compared to the previous result that had 5% gains. We are now seeing around approximately 17% or almost 13% increase in T-flops, right? And I mean, there is still loss. Initially, there is more loss, but as the training basically reaches the end of the execution, the loss is still is also becoming more acceptable in this particular case. Right. So and in this case, we are comparing the performance with baseline nickel, right? So the two approaches that we are comparing here are Z hybrid and Z using 24-bit model parallelism and 8-bit data parallelism, right? So basically going from 32 bits to 24 bits for model parallelism, this is basically less aggressive, and going from 32-bit to 8-bit, for data parallelism, where we know that gradients are being communicated, and we can go a little more aggressive. And as you can see, this is throughput samples per second. You can see this the baseline, the orange results are the baseline higher is better, and as for the 192 case, we the compression based approaches over MVAPICH are doing better than baseline nickel, around 7. The gains are different for different data points, but around 8% and almost 13% for on 192 GPUs. Right. So with this now, I'll move towards concluding my talk. And in this work, we analyze different communication routines, used by 3D parallelism approaches and zero stage one, which is basically now a typical training scenario. And in this, we propose two approaches called MZ hybrid and Z hybrid. So these are both two hybrid compression schemes where we are basically using lossy as well as lossless compression. And basically the two proposed schemes, they consider data sparsity, within communication and utilize these different compression libraries for different parallelism to provide training speedups and baseline, model performance. With MZ hybrid, it provides up to 4.4% increase in samples per second. And with Z hybrid, we saw around 20% increase in samples per second. So with this, I just want to reiterate one point that so maybe in this presentation, when we looked at lossless compression, maybe this is giving an impression that lossy compression somehow doesn't give that good of a performance. However, this is also very dependent on what kind of compression library is being used. So for lossy compression, we are using ZFP from Lawrence Livermore National Lab. That software is very well maintained, actively developed. So, there are new things and new features coming in. However, the MPC, on the other hand, it's not that actively managed. So maybe in the future, if we introduce support for a different lossless compression library in MVAPICH, then, maybe we could also see better performance with, lossless compression. And in this context, NVComp, which is an NVIDIA compression library, that basically is a lossless compression library, and it will be interesting to see some results with that. So with this, I thank all of you for your attention. This work is mainly done by Lang Zhu, who's a PhD student in our lab, and I just work with him on this. So I'm happy to take any questions if there are. Thank you.
Right. If there are any questions, please either unmute yourself and ask them, or raise your hand, or put them in chat. All right. Thank you very much, Aamir. Appreciate it.
Thanks. Thank you.